Alright, it's been a while since the first video on Project Ignition, but if you remember, last time I said that the sampling rate of the HX711 was a limiting factor, and that's why I wanted to use something else. And as it turns out, I didn't happen to come across any two-in-one ADC and signal amplifier combinations that would give a respectable sampling rate and an adequate signal amplification. So that's why I had to source the ADC and instrumentation amplifier separately. So the first step in that case was sorting out the instrumentation amplifier, which amplifies the tiny voltages coming from the strain gauges on the load cell to a value that an ADC can effectively detect. To understand what I mean by this, consider the HX711 for a moment. It's got a 24-bit ADC. So if the voltage supply from the Arduino to the load cell is 5 volts, we can do a simple little calculation to find the minimum detectable voltage per ADC count. So 5 volts is 5000 millivolts, and we have 2 to the power of 24 minus 1 steps from a 24-bit ADC, or counts. We do the minus 1 because we count from 0, not 1, and that gives you 0.000298 millivolts per step. And if you compare that to the millivolts per step from a 10-bit ADC, that number comes out to 4.88 millivolts per step. So we can see that's a huge difference. But from a pure voltage perspective, it might seem like, yeah, either or is pretty good because you can detect very small voltages, but that alone isn't enough to say whether we can or cannot capture small fluctuations from a motor or thrust source in general, which to begin with may not produce much thrust, like in the case of the D motor. Think of it like this. We need to marry the ADC and the instrumentation amplifier. They need to be compatible with each other because if the instrumentation amplifier doesn't amplify the voltages to what the ADC can detect, you ain't measuring nothing. So you can either find a higher resolution ADC to cater to a possibly low gain amplifier or get a better instrumentation amplifier altogether. And keep in mind that bumping up the ADC resolution is generally going to come at the cost of the sampling rate, unless you're willing to dish out some serious cash. So regardless, you need an instrumentation amplifier first before you go hunting for an ADC. Now, I recently got myself a Texas Instruments INA333 instrumentation amplifier, well, it on a breakout board, and hooked it up to the load cell and the Arduino. Now, it might look crazy with so many different colored wires, but the connections are quite straightforward. The Arduino supplies 5 volts to the load cell and the INA333. The white wire from the load cell, which is also called a signal minus, goes to the voltage in minus on the INA333, and the green or the signal plus from the load cell goes to the VIN plus or voltage in plus on the INA333. Vref or the reference voltage is hooked up to ground, and Vout is the amplified voltage we are interested in, and that goes to pin A0 on the Arduino Uno or the multimeter depending on where I want to read the value from. Now the bare INA333 chip alone also has 8 pins, but 2 of them are RG pins, as you can see from the photo in the datasheet. This is where you're supposed to hook up a resistor to set the gain, or in other words the amplification factor of the signal. But because I've got a breakout board here, it instead has a silver little thing which is a trim pot which you're supposed to twist to set the gain. Alright, now I'm going to be taking a series of measurements using the multimeter to see how the millivolt per gram ratio varies with load. It should be linear, but we'll see what we get. And because I didn't have masses in set increments, I've just gone on and used whatever I had sitting around the house. So first up, I've cranked the trim pot to minimum gain, and this is giving out a good 1.66 volts. And at this setting, if I put this bit of mass, which is nearly a kilo, it barely registers the change in load. And that 0.001 or 2 bit of change is anyways going to be masked by noise in the system and from the measurement. And I also, for the same test, printed to the serial monitor what was coming off pin A0, and you can see it's much more noisier than the multimeter reading, but it's sitting around a good 1620-ish millivolts. So What I've done next is crank the trim pot to max gain, and now the zero load reference voltage, well, zero load apart from what's already at the free end, we're getting 1.32 volts roughly. And now if we load the free end, we should hopefully see some change in the voltage. So starting with this orange thing, which is about 12 grams, we've got a change in the voltage. We are now sitting at 1327 millivolts, 1327, 1328. So that's good. Next up, with this 19-gram stick of solder, we move up to 1331 millivolts, and then with a 53, 54 gram glue stick, we're getting 1345 millivolts. And for the next test, we're going to bump up the mass to 105 grams. There and there. And now we're getting 1366, 67. And then for this 200 gram mass, well, 203 to be exact, we are getting 13. No, not getting anything. We're not even put it on yet. Getting 1408. Next up is this 378 gram cup, and we get 1478 millivolts. Now with some water in the cup, we have a 633 gram load, call it 635, and if you put that there, we have 1.593 volts. Cool. And we've got the ring again, which is 970 grams roughly, and with that you get 1735. And last but not least, we've got the water bottle, which is about 1.983 kilos. And if we put that on very carefully, we are registering, once we get the right setting on the multimeter, 2.17 volts. All right, so that's that. I guess it's worth noting that this little experiment did not count for any temperature effects, although it was done in a stable indoor environment. And I did run another test, like a similar test, yesterday as well, and the zero load reference voltage I got then was slightly different at 1.367 compared to the 1.32 we're getting right now. So I guess it's not the most high-tech piece of equipment, but seems to work fine, for now at least. Anyways, plotting the data points, we get this graph, and right off the bat we can see that we have a millivolt per gram ratio that scales pretty much linearly. And for this test, the gradient we're getting is 0.42 millivolts per gram. And with the other test, I had a gradient of 0.37 millivolts per gram. So I guess you can say it's around the zero point 0.4 mark for this setup. Actually, now that we've got our sensitivity of 0.42 millivolts per gram, so that's a 0.42 millivolt change for each gram added to the load cell, we can go on and calculate the number of grams represented by each ADC step. So given the 10-bit ADC and a 5-volt supply, we have 0.42, that's millivolts per gram, divided by the 4.88, which is the minimum detectable voltage per step. Um, and so taking care of the units first, we have millivolts, and that cancels. Left with 1 over grams over 1 over step, which turns out to be steps per gram. And 0.42 divided by 4.88 comes out to 0.086 steps by the ADC to represent each gram of load. And what's more useful, or more understandable, is the grams per step instead. So you just got to go 1 divided by that number and you get 11.61 grams per step, which, if you consider like a D12 S-test motor with a peak thrust of around 3000-ish grams, is okay, well, I think. But at the same time, there's no harm in going for a higher resolution ADC and or a higher gain instrumentation amplifier if you can find one. But you just got to make sure that when you do go for that higher gain amplifier, you don't set the gain so high that the output is getting railed. What I mean by that is make sure you can represent the max load you're intending to by staying within the supply voltage range, else your signal is going to get clipped. So I don't think this will be a problem in this case because it doesn't feel as if the gain you can play with on the breakout board is, all that much. I mean, the actual chip has a configurable gain of 1 to 1000, but that's via the RG pins, which this board doesn't have. So we have a reference voltage of like, what was it, 1322 millivolts. And if you take 0.42 millivolts per gram of sensitivity and you're expecting like a max thrust of 3000 grams, you get 1260 millivolts. So that means to represent your max thrust coming from the motor, your signal will require or will be at roughly 1322 plus 1260 millivolts, which comes out to 2852, so about 2.58 volts. And that's well below the supply voltage, so we should be good. Anyways, that's it for this video. I'm going to try the INA333 and a few analog to digital converters and see how it goes. And if that doesn't work out, I'm probably going to move on to a different instrumentation amplifier. So don't forget to like and subscribe, and I'll see you in the next video.